Thank you for coming for my talk here. So yeah, as introduced, I'm Jehyuk Jang. So and you can just call me Jake, and I'm from Tokamak Network. Today I'd like to talk about the ZKP for everyone, and we will explore how to apply ZKP to your some random transactions, Ethereum transactions in a few clicks. Yeah. Yeah. Here's what we will cover today. First, I'd like to briefly introduce the technical things to zero knowledge proofs, and then some key considerations when designing your ZKP. And finally, we will propose our new approach for easier and faster ZKP utilization. Right. When you Google ZKP, you may find many technical articles that praise that ZKPs are magic, kind of magic. So, in my opinion, no, they are not magic. They have clear limitation in some theoretical limitation, and their limit stays within the bounds of the classical information theory, which was established in 1940 by Claudius Shannon. And also, in practice, when it comes to applications to the Ethereum, the ZKPs are just reshaping the scalability trilemma, this triangle, and they don't expand this triangle. They can't expand it. They just reshape. They are just tools. So yeah. So I'm going to deep inside, get into the ZKPs, and to this end, I think I need to take an example of the use case for the ZKP. So I think the best use case, one of the best use cases for ZKP can be said as verifiable computation. So in this scenario, let's say there is a computation, a big and huge and massive complex computation, and you are going to outsource. You don't want to do this yourself. Instead, you are going to outsource this computation to a worker or prover. So in this scenario, the worker or prover will give back you the output of the computation along with the proof about the correct execution of this computation. Yeah. And so the key point here is how to make the proof. How can you guarantee that the proof guarantees the correct execution of the computation? So I'd like to say the entire procedure of making the proof in 3 steps, like compile, commit, and prove. So first we need to compile the computation itself to generate the circuit. So here the circuit can be said as a list of constraints, and with this constraint you can check that if the computation was correct or not. And given this circuit, we need to commit the result of this compilation. So the commit step commits the circuit. So the resulting commitments will be the compressed representation of the circuit, and also these commitments, cryptographic commitments are some kind of cryptographic agreement on the integrity of this circuit between the prover and verifier. And then finally the prover can generate the proof, and this proof can be verified by a verification which comes from the commitments. Yeah. This is the entire procedure. And here we might have there are some security considerations we need to take into when we designing or utilizing a ZKP. The potential security leaks can come from the first two steps, compile and committing, because the fundamental theories behind the ZKP system does not cover the security of the compile and commit, so they are out of the ZKP coverage. So we need to be very careful when you compile and commit. So I'd like to say there is a trade-off between the security and efficiency when you're using such ZKP. So depending on the usage of the compilers and commitments, if the system has more frequently uses compilers and commitments, that may lead to faster proof generation and easier privacy. But the ZKP system will require more reliance on the trust in the compilers. And conversely, if we use less frequent use of the compilers and commitments, the proof generation will be slower, but the trust requirement dependency in the compilers will be less. So this can be a trade-off when you're using the ZKP. And so this is the main topic today. So if you just want to apply ZKP to any random transactions, do you need to take all those things into account? So I'd like to say no here. So at this point, I'm going to propose our new ZKP system called Tokamak ZKP, which has some good properties like this. Which has easy to use graphic user interface, and also has fast proof generation, and has low memory requirement and chip verification as cheap as other snarks. So with our Tokamak ZKP, you don't need to build circuits on your own. So you're free from compiling some things. And you can generate a proof for any random transaction just in few minutes on your home desktop. Right. Then I'd like to say what makes this efficiency. So I'm going to compare our system with some traditional approaches like zk-EVM, designed by the PSE and Scrolls. They are famous. And yeah, in their approach, they compile the entire EVM into a massive circuit. And these circuits should be massive and large enough so that it can prepare for all uncertain and unpredictable computations that can be handled by the EVM. That's why this circuit cannot help avoiding the size expansion. But in our case, we adopted some two-step compilation approach to reduce the uncertainty involved in the circuit. So we have two compilation approach steps. For the first compilation, we compile the EVM, especially not the full EVM, but just static parts of the EVM that is very predictable. So because there are no dynamic things or unpredictable things in the circuit, the resulting subcircuits must be very small. And once you get some contract and method of interest, you can compile it once again, so that we will generate the wiring of these subcircuits that can represent this contract, the computation in this contracted method. So this is our approach, and right. So here I just summarize the input and output of the Tokamak ZKP. So as a result of the first compilation, we can get some the commitments to the EVM subcircuits, which is called CRS. And these CRS can be reusable for various contracts and computations. And next, for the second compilation, we can get some commitments to the subcircuit wiring, which is called BP. And this BP is reusable for some various instances as long as the contract method is fixed. That means if we want to generate some transactions coming from the other contracts, then we need to rerun the compilation again. Yeah. All right. And here I prepared a demo how to apply our Tokamak ZKP system to random transactions. And I'm not sure if, I think I cannot play. Oh, thank you. Yeah. So here we provide a simple graphic user interface to use our ZKP system. And for the very first step, we need to run the first compiler here. And then you need to run setup to commit to the first compiler result. Yeah. And then you can just enter the hash of the transaction you want to apply ZKP, like this. Yeah. And then you run the second compiler. Then we need to commit to the result of the second compiler. Yeah. And finally, you can generate a proof using this proof algorithm about the correctness of the selected transaction. Yeah. And you can verify it. Yeah. And you can choose another transaction to run it. Here, what I want to show you is that the commitment to the second compilation for different transactions can be skipped. Yeah. Because the second compilation can be reusable for many other different transactions. Yeah. Yeah. Right. Then let me introduce how to use our ZKP system for better Ethereum ecosystem. So this is kind of potential application to Ethereum. So just consider the situation where we want to operate some layer 2 channels, not the roll-up network, but just channels. And suppose that this channel is specialized for limited computations or predefined computations. So in this case, we can use our ZKP system. We need to run the two-step compilations first, right? So the first compilation and commitment can be run on-chain. And once we fix the type of computation, the type of transactions to run, to execute, then we can run the second compiler and commitments on the on-chain before opening a channel. So once this the type of transactions is fixed, then the users can open a channel, their own channel, on which they can run the transactions and generate proofs. Yeah. And in the second channel, the users do not need to run any compilers or commitments because they are done on-chain already. And once the users are satisfied with their purpose, then they can close, they can aggregate the proofs, and they can close the channel, and they can send back the result to the on-chain. Then using just the single verification equation, you can check everything about the layer 2. Yeah. This is our scenario. Right. So here I'd like to conclude with some key takeaways. Yeah. So when you're designing a GKP, or unless you want to utilize it, you can't have everything. All snarks and stocks have a trade-off between efficiency and compiler dependency. So with our tokamak ZKP system, it is easier to use and faster and lighter through our two-step compilation. So our next move in the future will be to provide a DIY tool to launch, and that enables any users can launch and operate computation-specific state channels or rollups for to keep their privacy. Yeah. Yeah. And if you're interested, you can download a graphic user interface that we provide, and you can go through our paper for theories, and also we have some GitHub codes. Yeah. You can find them easily. Thank you. Thank you for your time. Yeah.
Okay, do you have any questions? One question.
You said about the proof aggregation on the L2 to L1. How long does it take for it to complete?
I'm not sure. It's just an MSM. It will be just an multiscalar multiplication. So it can be done quickly if you use some GPU. Yeah.
So it depends on the GPU?
Yeah, right.
All right.
Yeah, very quickly can be done.
Thanks.
This leads to my question about GPUs and ZK proofs being very compute intense. I believe that they're definitely the future, but optimistic rollups are quite popular now just because they're easier to implement, cheaper to implement. Can you just tell us a bit more about this broader idea of like when are we actually going to have implementable ZK proofs that are comparatively cheap and easy to implement?
Just I think we can open some service from next year, maybe, hopefully, yeah. So you can meet very easy to use and very, yeah. You can run it from next year, I think, yeah.
Do we have any more questions? Thank you. Thank you so much.
Thank you.